Jacobian singularities, and I talked about dynamics. Today I'll talk about biped locomotion, which is an applied area. Okay, so I'll just share my screen. Yeah, so I hope this is visible, right?
Yes, sir, it is visible, sir. It is fine.
Okay. Okay, so I'm audible also clearly, right?
Sir.
Okay, so I'll talk about biped locomotion, which is an interesting topic in robotics research. So I'll try and go with the introduction, then a few areas of research, and then we'll look at some application areas. So biped locomotion, as the name indicates, is basically walking. So you understand what is walking. We all walk. Animals move from one place to another place, and birds fly. So this all comes under what we mean by locomotion. Okay, so locomotion is basically meaning moving from one place to another. So moving from one place to another is basically called locomotion. And the best example of locomotion is this one, which we all have, we all do in our daily, almost every day. Now, so locomotion means moving from one place to another, and there are different ways by which animals and robots today move. For example, a fish swims, which is also a part of locomotion. A dog can run or jump around, that is also locomotion. A bird can fly, that is also locomotion. So in terms of robotics, we have robotic fishes, we have multi-legged systems, we have aerial robots, which are locomoting. So that is the very basic meaning of the word locomotion. Now, today's talk, I'll basically talk about introduction to legged locomotion, the robotics legged locomotion, especially how we have evolved in the area of legged locomotion. Then passive and dynamic bipeds. These are two classifications in which bipeds are divided. Then optimal design and gait. How do you get optimal trajectory when you're walking? Now, again, you would have studied inverse kinematics, and in terms of degrees of freedom, this system has very high degrees of freedom. In our legs, we have about 16 degrees of freedom. Okay, so this system is very redundant, which means that there are infinite inverse kinematic solutions for doing inverse kinematics. So which solution are you going to take? So how are you going to determine that? Then motion planning in 3D, when we are walking from one point to another point, how do we go from one position to another position? That is what we mean by motion planning. So today's talk, I'll start off with basic introduction, then I'll move on to uh, research issues and in terms of design. Now, first of all, why should we study biped locomotion? Okay, what is the point? First of all, we need to look at this question. So understanding biped locomotion will give us an understanding of biomechanics because we are walking, right? We walk. So we need to understand this biomechanics of walk. So if you understand biomechanics of walk, we can design robots which can also walk. Now this walking can be four-legged, it can be two-legged. Okay, but it gives us more advantages in the sense we can design prosthetic devices. For example, for you can design artificial feet, you can design knee joints, ankle joints, legs. Then you can also understand the effect of diseases. For example, when you're walking, you have something called a gait. So when you have a disease like arthritis, what happens to your gait? So simply by looking at your gait, can you tell if a person has arthritis? You can actually do that. Okay. So understanding biomechanics of walk has a lot of advantages. Now, strictly in the sense of robotics, robots living in society need to have human-like features. Today we have a lot of social robots. So these robots need to have human-like features. For example, they have hands, they have legs, they have face, and they walk around. So you must know what is walking. And uh, they should behave like humans. Okay. Now, all man-made structures are designed for human habitation and human locomotion. So our buildings, roads, cars. So this robot should be able to walk like humans because all our structures are designed for humans. Then we have the last, but a lot of companies in that area now. That is entertainment, movies, pets, robot human cooperation, rehabilitation. So there are a lot of robots which are coming in movies. Okay, in India also. Now these robots should be designed like humans, and they should behave like humans. Otherwise, half the fun is lost. So it's a question of designing like human. It's a question of behaving like human. So we are also learning about ourselves. Now, it's an interesting thing that if you look at biology, biology prefers legs, not wheels. A wheeled mobile robot is more energy efficient, but in biological systems, you'll never find wheels. A dog or a man or a bird or fish, they never have wheels. They always have legs. Now, legs require more energy, but the advantage being that they are multifunctional. The wheels are not multifunctional. That is the reason why biology prefers legs. And recently, there has been a lot of interest in legged locomotion, essentially because they are technically feasible. So biology prefers legs. The advantages of legs is compared to as they can walk over obstacles, they have less footprint area, and body can maintain at the same height for vision, and it can perform different functions like climbing stairs, sitting down, lying down, etc., which a wheel robot cannot do. So there are a lot of advantages of studying biped locomotion, and if you just look historically, the word robot actually came from Karl Kapek's play depicting human-like mechanical men, right? So he's the first person who wrote this play in 1921, that in future there will be mechanical men like this who are going to replace human beings in industries. And he used the word robot, which essentially means mechanical men or labor. Okay. That's where the word robot came from. But he also said about, in his play, it is basically about a bipedal system only. Okay. Then comes Isaac Asimov, 1942. He first used the word robotics, where he talked about robotics, that in future there will be a subject called robotics and all that. And most of his, if you read his books, they are basically to do with humanoids. Okay? And humanoids are again bipedal systems only. So historically, bipedal systems have been in robotics for a very long time. Of course, till 1950, there are no robots. So this is all science fiction. Okay? But it is bipeds. Now, when we are talking about legged system motion, the first thing that comes to mind is if you're designing a system or you're thinking about two-legged, four-legged, then how many legs will you have? And what is the position of the legs? Will you have two-legged? Will you have four-legged? And if you're saying four-legged, we'll start off with four-legged, then we'll go to two-legged. So in four-legged cases, how the body is going to move is different. For example, in the case of a mammal, in the case of in the case of animals which are moving forward, like a dog, for example, it goes forward in this direction. But if you look at a crab, okay, then the crab goes sideways. Okay, so although they have four legs, they move in different ways. Okay, now if you have four legs again, should the legs be sideways like this, or should the legs be straight? This is the case of a horse, for example. Okay, the legs are like this for a reptile, but for a horse they are straight. Okay, so although these are four-legged, they behave in different ways. So now we have basically evolved, and this evolution has given us the way we are going to, the way we behave, based on the task we are performing, based on energy requirements. So this is the case, the design of a leg for a mammal, and this is the case of a reptile, for example, a lizard. Okay, the legs are sideways like this, whereas for a mammal, like a horse, the legs are straight down. So what is the reason? If you think a little bit. Now, then the next question is shape of legs. Okay, so we are saying that the leg for a human is like this. Okay, but the leg for a reptile is sideways like this. The legs for an insect. So this is an insect leg. Insect leg is like this. For a cockroach, it is like this. So why is this different shape? So different number of leg, different shape of leg, different position where it is fixed. What does this have to do? So if you think a little bit, our legs are like this. Why is it like this? Because if our leg was like this, okay, sideways, then what would happen is when we are standing, this motor here or this muscle here would have to support this joint torque. So if our leg was sideways, then this joint here is subjected to a very high torque because of this moment arm here. Okay. Whereas if it is fixed straight down like this, what would happen is the mg force here is going to get divided into mg by 2 and it will go straight onto the ground and there is a reaction force. There is no moment about here. Okay. So if you look at the same situation, if it is like this, what is happening? Because mg is acting here, there is a big moment arm here. Okay, so there is a very high moment it has to support at this joint. Okay. That is the reason why our legs are straight forward. And in the case of a horse or a dog, we spend most of our time standing, a lot of time standing, and because of which our legs are straight down. And you require lesser energy. What about this fellow then? The reptile. So this is a lizard, a house lizard you must have seen. The leg is like this. So what in the case of the lizard? Now the lizard has to climb walls. Now if it has to climb walls, what will happen is this distance should be very low. Otherwise, it will have to support a very high torque here for climbing walls. So the body should be very close to the ground. So the torque requirement is reduced. And that is the reason why the leg is like this. What about a cockroach? The cockroach leg is like this. Okay. Now these cockroaches are insects, and a lot of insect legs are like this. Why? Because insects are eaten by other insects or other animals. So the safety is the most important for them. So they have to maintain their body very close to the ground because they have to climb walls, go vertical on vertical surfaces. But they should be able to generate very high torques to escape. So if you disturb a cockroach, it will run in another direction, and it's very quick. Now, why is it very quick? Is because it has this very long moment arm, and it can generate a very high torque and change direction very quickly. Okay, so that is the difference between a mammal, okay, lizard, and an insect. They all legs, different shapes, different energy requirements for survival or for performance. Okay, so this is basically trying to explain that we can have different number of legs, we can have different shape of legs. It depends on what is the objective that you're trying to do. Now, for a mammal, our legs are straight down, and for a reptile, the legs are in the side like this. Now, even for two-legged systems, we can have legs which are bent inwards, or legs which are bent outwards, or which are bent like this. Which one? Okay. Again, the same question: stability, energy requirement, task requirement. So before you design a robot, you have to get these things clear, that what is it you're trying to do, how many legs are there, what is the energy requirement, which one is giving you minimum energy. So this is a completely process optimization, and we have evolved over the millions and millions of years due to evolution. Now there can be different relative length of legs. So this is a spider which has 8 legs, or an insect with 8 legs, and all the shape of the legs are different, you can see, and the lengths are different also. Okay, and it walks in a particular pattern which is called the gait. So all these parameters, number of legs, shape of legs, length of legs, these are optimization parameters when you're trying to design a robot. What about a tail? What is the use of tail? Tail is used for balancing. Okay. So in this configuration, you can see very easily that it can move the position of the CG forward or backward by stretching the tail in this direction or by stretching the tail in that direction. So the effective CG point moves this side or it moves this side. So for balancing, it basically uses the tail. Now insects which do not have arms can use the tail for getting up. So for example, if the insect falls down, the insect can again right itself or get up by using the tail. So each of these systems, or each of these elements, legs, tails, they have a function, and we have evolved like this. Okay. So what I'm trying to do is, so in terms of robotics, the most advanced quadruped built, after this I'll move on to biped, is the big dog. You might have seen this in videos. Okay. So this big dog is a quadruped robot, which is built which was essentially built for the army, the US Army, and it can go in any kind of terrain. If you look at the shape of the legs, the sequence in which the legs are moving, they are moving alternately and diagonally, if you can see that. Okay. So all the diagonals of legs are moving at a time, and this has very high stability. It can go on any kind of surface, okay, like very slippery ice. So let's look at, so it is exceptionally stable. So this shows some of the challenges in design of locomotion systems, either in terms of just design, in terms of control. So work on ice, walking, running, it is able to go on any kind of terrain. Okay. So this is the most advanced quadruped system which has been built. Now, what do you mean by gait, or what is balance? So balance is essentially when the quadruped or the multi-legged system is walking, the legs on the ground will be forming the leg support polygon. Okay. And the projection of the center of moment or center of mass should be inside that polygon. Then the system is balanced. Now, if the if the center of mass goes outside the polygon, the system will immediately fall. That is what we mean by balance here. Okay, and so the pattern of foot placement is what we call gait. So they will move their legs in such a way that the projection of the center of moment is always inside this foot support polygon. Okay, for a quadruped, hexaped, or for a biped, it's the same example. So this is what we mean by a gait. So how is gait done? Gait, this is called a gait diagram, and how it is drawn is essentially this is my legs. So left back, left forward, right back, and this is time instance T1, T2, T3, T4. Okay, it starts off with all four legs on the ground. Now, in this particular case, the black line indicates leg on the ground. So the left back and the right forward is on the ground. So it is dark colored here, just black colored. The other two are in air, so it is not there. Okay. Then the next instance, what it does from here to here, all the four are on the ground. So you can see all of them are black here. Okay. Then the next instance, what will happen is the remaining two will go on the air. Okay, so it is alternating between two legs. These two are on the air, then these two are on the air. Okay, so two in air, four on ground, two on air, then again on ground, and then it will alternate. That is what we mean by a gait pattern. So bipeds, quadrupeds walk by using different gait patterns, and the gait patterns can be of different types. For example, at one time you can lift only one leg and move the body forward, or you can move two legs alternately, and if you're running, it can be all legs also. So depending on which gait pattern you're using, based on that, we are going to move the body moves forward. Okay. So these are various gait patterns which can be used for running, jumping, walking by quadrupeds, and they have particular names. Now, how do we start off with this analysis of quadrupeds? Essentially, we assign a global frame. Okay, so this is my global frame, and with respect to the global frame, I put a local frame. So this is my 000 for the robot. And with respect to the local frame here, I write my DH parameters and proceed with the links like the assignment axis for each leg. Now, if I consider this point to be 000, then this one is actually something similar to a robotic arm, like a serial arm, I mean. Okay, so we can model this by four serial arms, all of them which are meeting here. So whatever kinematics dynamics you have done is also applicable here. The only point being that you have to put a 000 suitably so that all the other it can take care of the legs by means of serial arms. Okay, then you follow a gait pattern. How does it move forward? In this particular case, three legs are on the ground, so those three are on the ground. This is the leg in air, so it follows a trajectory in air, and as the leg goes forward, the body also moves forward slowly. And that's how it is moving. Okay. This is how it basically moves. And this is an example of a simple robot quadruped which has been built to move forward. Now, what is the gait pattern it is using? You can see it is moving it is having three legs on the ground and one leg is going forward. And using that, it is able to go forward. This is a very simple robot. It is made with the servo motors with an Arduino processor. So these robots can be made very simply, and they are very, very cheap. This one hardly would cost 2,000-3,000 rupees. Okay, and you can study all kinds of things like gait pattern genesis, motion planning, etc. Now, coming to bipeds, bipeds can be classified into two major groups. One group is what we call, okay, these two groups are based on the energy requirement. For example, when the biped is moving forward, are you having to give it energy? Now, if you have to give it energy, then it is called an active biped. So the robot on the left side is an active biped, and it has motors in the joints, and these motors give it energy, and the robot moves forward. So to move forward, to do work, you have to give it energy, right? Now, is it possible to have a bipedal system without motors? Okay, yes, it is. But you still have to give it energy because it has to move forward. Where is the energy going to come from? So, for example, gravitational energy. So, if you put a biped in an inclined surface, what will happen is it will go down. And such bipeds which do not require energy or motors are called passive bipeds. Okay, so this is an active biped and this is a passive biped. Now, how do passive systems work? So the earliest bipeds which were studied, 1980s and that time, so these were all passive bipeds. And how does it work? So if you look at how does a wheel rotate down, so we have a wheel, okay, I'm drawing a wheel here, and the wheel is resting on a surface, on a flat surface. Okay. Now, it will not move. Why it will not move? because if I take the center point of the wheel or the CG of the wheel, the force coming down is mg, okay, and the contact point is also here. So the projection of the CG is going through the contact point, and there is no resultant moment at that point. Okay, the down force is being balanced by the upward force, and it is in equilibrium there. Okay, so the wheel, if you keep on a flat surface, it will not rotate. But the moment I keep a wheel on an inclined surface, like the one shown here, so this is the wheel, the projection of the CG is coming down. This is my mg, okay, but the contact point is somewhere behind here. Okay, the figure on the left side top. So what is happening is this force into that distance is creating a moment about this about this contact point now. Okay, and because it is on an inclined surface, what is happening? This moment is ensuring that the wheel rotates forward. That's how our wheel rotates. Where is the energy coming from? The energy is gravitational energy. It's G. So if we can make a system which is going to harness gravitational energy and design it like a wheel, then it can move without any energy. Okay, and such robots are called self-propelling systems, biped robots, passive robots. They mean the same thing. So the earliest robots were this passive robots, and they moved forward. They were designed like a wheel. Now, if you look at the design, this is like a wheel. The two legs. This is the wheel. This is like a, okay, and this is, and they're like the spokes of a wheel. If you see the spokes of a bicycle wheel, they're on the center and they're like this. So if I cut it here, if I cut it here and I cut it here, then these are two legs, and this is a part of a wheel, and it will go forward if I keep it on an incline. And this is the idea of a biped robot. This is an example of one that was made. So you can see the legs are in the form of are circular, and they have two inclines. And if you keep it on an incline, it will just walk forward. Okay, where is the energy coming from? It is coming from gravity. And the earliest robots were of this nature, and they are very simple to make, very interesting in terms of dynamics, to understand how a dynamic system moves forward. This is another one. So this is a passive walker which can walk down a slope. It doesn't require any energy. So no motors, it is walking. Where is the energy coming from? It is gravitational energy. Okay, but it cannot walk on flat ground. It has to go down a slope. So these are interesting because they can walk without energy, okay, but only down a slope. This is a toy which in our class in dynamics, in robot dynamics, we ask the students to make this one. And if you make this, you can make it with wood or with plastic or with cardboard. And this will give you an idea of passive walking and how it works. So if you look at the legs, the whole system is walking forward, okay, with no energy requirement from motors. It is using gravitational energy. So this is a very interesting device to understand dynamics of bipedal systems. Okay, you can make it and see. Now, bipedal systems are inherently unbalanced. They are dynamically unbalanced systems. What is the meaning of that? It basically means that if I have this one, like a one-legged robot, it has 2 degrees of freedom. One is it can rotate about that point. There's an actuator there. It can rotate, so it can change the angle like this or like this of the body. And the second is there's a passive spring there. So there is a distance here. So there is a theta variable and there's a d variable here now. Okay. So by controlling these 2 variables, you can actually make this fellow work. Okay, how? We can see this. Okay. So what we are seeing is that this one-legged robot can go forward or it can go backward. It can jump in one position simply by changing that theta and d, with 2 variables. Okay, but it cannot stand in one place. If you want this robot to stand still in one place, it cannot. Why? Because it's a dynamically unbalanced system. Okay, so the moment it tries to balance, it will fall. It is only balancing by dynamically balancing itself by changing the d and theta. Okay, so a bipedal system is essentially a dynamically unbalanced system. The other, and why it is, because if it tries to stand like an inverted pendulum, okay, if it tries to stand still in one point, there will be a resultant moment in some direction and it will immediately fall. Okay, so this is what we mean by dynamic balance of a bipedal system. And how do we control this 2-legged system? We basically, one-legged system. We control it by controlling that angle. So there is an angle, body angle there. So we can have a PD controller and then control that body angle. which can control the angle of this body with respect to the horizontal. That's one. The second is we can control the length L here, okay, by a PD controller. So essentially we can control the motion of this one-legged robot by controlling these two variables. Now these are modeled by means of what we call a finite state machine. What this basically means that there are different states which are not connected to each other. It's not a continuous kind of a system. So we are going to model this as a finite state machine. So there is a flight stage when the leg is in air. Then there is a loading stage where the heel touches the ground. So there is a loading stage. The spring gets compressed. Okay. Then there is the heel and the toe contact is made. Okay. And then there is a toe off stage where the spring is. So let me explain it here. So this is the way it is. There is a spring. So first it's in air, then this one is compressed, then the spring is expanded, and this goes back into air. So in these different stages, each stage is a finite state of the system. So it is going from one state to another state in a particular cycle, and that's how we are controlling it. Now, in terms of biped locomotion, several robots have been built. For example, the one-legged robot also has been built. It was there for a very long time. The only thing it is unstable. Then people Honda built the Asimo robot, which has about 54 degrees of freedom, and it can walk, it can balance, it can talk, and do all kinds of things. Now, after this 2018, the most advanced bipedal system which has been built is the Atlas robot. So this is basically for historical purpose to show you that it is going from a passive walker, 1980s, to something which is very, very complicated and exceptionally, in terms of technology, probably this is the best bipedal system which has been built so far. So it can walk on any kind of terrain. It can build its own map. So it is extremely difficult for this robot to walk in. It is difficult even for a human being to walk on conditions like this. Okay, so this is the Atlas robot 2018, and probably the most advanced robot in the world today, bipedal system. So let's look at a little bit more serious talk, that how do we analyze bipedal locomotion in terms of robotics? Okay, how do I design the gait? What is balance? So we'll be looking at issues like balance. What is gait? Before that, what is gait? What is balance? Using zero moment point. Then what is in terms of dynamics? Okay, what is a trajectory, optimal trajectory? What is motion planning? These are some things which we will see in terms of more serious talk. So when we are walking, it's interesting that this is a human being. We walk like this only. So you walk, I walk, we all walk like this. And as I was talking in my previous lecture, that although there are infinite solutions to this problem, we all walk in the same way. It means that we have evolved such that we are all at energy optimal. And that is the reason we all walk in the same way. So this bipedal walk can be divided into two groups. It can be seen in two planes. One is the frontal plane. So if you're standing in front of a mirror and you're seeing yourself, then what you'll see is in the frontal plane. This is the frontal plane. So this is my frontal plane where you can see yourself. Now there is a side plane or a sagittal plane. So if you're looking from the side, from the side, then that is my sagittal plane. So we are going to divide this walk in two parts, into two views rather. So these two views are the frontal view and the lateral view. Okay, and then analyze the walking pattern. Now in the two patterns, if we see, first we are in two-legged stance. You're standing in two legs, as shown in the figure here. Then we move to one direction. So we move the body to one direction. Why do we move it to one direction? To ensure that the projection of the center of gravity is falling inside the foot on the ground. So in this position, projection of CG is there now. Okay, so your CG is on your foot on the ground, so you're balanced. Then the leg goes forward. So this is all the leg going forward. Then contact is made. Okay, you're on two-legged stance, and then again you can see that the body moves on the other direction now. And again the CG is on the leg on the ground, and then the other leg goes forward. So for a two-legged system, the gait diagram is two leg, one leg, two leg, one leg, two leg, one leg. Okay, that is the gait diagram. That's how we move forward. In the frontal plane, this is the front plane. Now in the side plane, Okay, what we are seeing is that correspondingly, when the two legs are on ground, the rear leg goes forward and it becomes the front leg. So this is the rear leg, it is going forward and it has become the front leg now. So it is two leg stance, the rear leg goes forward, becomes the front leg. Then it's on two leg again. Then again it's on one leg, the rear leg again goes forward, this is the rear leg again. Going forward, it becomes the front leg. So this is what we mean by gait of a bipedal system. And if you're looking at the two planes, this is the front plane and this is the side plane. So you can stand in front of a mirror and see when you're walking, what you'll see is this moving from side to side, two leg, one leg, two leg, essentially to bring the center of pressure onto the leg on the ground. The black point there is the center of pressure. Okay, so this is in the front plane. In the side plane, okay, the rear leg comes forward and becomes the front leg, and the leg on the ground supports the projection of the center of pressure. Okay, so this is how, or this is the gait diagram for bipedal walking in the front plane and the side plane. Now, so this is being done essentially to ensure balance. So the next question comes, what is balance and how do you ensure it? So balance is ensured by what we call a zero moment point. And by using, this is a dynamic system. So we can, by doing dynamics, we can analyze this system. So this is a two-legged robot. Let us say that leg is on the leg on the ground. Okay, and this leg is leg in air. Okay. So each of the links are lumped masses. So these are all black ones are all lumped masses. So each of the masses are subjected to a gravity, which is pulling it down, and acceleration in that particular direction. So if it is moving in a particular direction, it will be subjected to forces in that direction, inertia forces in that direction. So each of these masses are subjected to a gravity force and the inertia forces. Okay. So the resultant is a difference between the mg minus ma in terms of forces. Now, in terms of moments, at this point, there is a moment which is acting. How is the moment? So all these mg forces, resultant forces, suppose it is here. Okay, so this is my force. So this force into this distance is a moment now. Okay, so each of these lump masses will be subjected to forces, and that force into the distance will cause a moment about that ankle point now. Okay, so we have two equations. One is a force equation, one is a moment equation, right? Now, in terms of the forces, all the forces, because of the lump masses, will have a resultant which is in that direction at the ankle. Okay, so it need not be at the ankle point, it can be somewhere else, but it has to be on the foot. Okay, and by Newton's third law, what will happen is there will be an equal and opposite reaction which will balance it. Okay, so the forces do not cause any disbalance, the forces are balanced. But what causes a disbalance is the moments. Now, there is a force acting like this, and there's a resultant force here. So this force into this distance, okay, has to counteract whatever moment is coming in that direction. So whatever moments are coming, there will be a resultant moment about the ankle point. Now that has to be counteracted by the moment caused by the force coming from the foot, acting at the bottom of the foot into that distance. So if this moment is balancing this moment, then the system is balanced. Okay. And that we can find it very easily. From the moment equation, we can basically write the moment equation and find out the moment divided by that force will give us a distance. So this is my distance. Okay. What distance? This distance. So this is my foot. This is my ankle. So that's my ankle. So there is a force acting here, and there's a moment here. So this force into that distance must counteract the resultant moment there. Okay, that is the meaning of this distance. And this is basically called my zero moment point. So this is what we call by a zero moment point, or ZMP. Now for balance, we have to ensure that the zero moment point is inside the foot on the ground. It can be anywhere, but it's on the foot on the ground. The moment the zero moment point comes out, it will fall. It basically means there is a resultant torque now, and it will fall in that direction. So when we are making the system balanced, we have to ensure that the zero moment point is in the foot, inside the foot polygon, and we can compute it this way. Okay. Now this is a two-legged robot. You can see this is a 3D view. The previous one was two different views. The black dot is the zero moment point. So the leg on the ground, the moment point has to be on that. The leg is on the ground, the rear leg goes forward, then it comes on two-leg stance. The moment it is on two leg on the ground, the zero moment point shifts to the other foot. So the zero moment point is shifting from one foot to the other foot depending on which one is on the ground. You can see that. So it's this side, then it goes that side, then it comes this side, then it goes that side again, then it comes this side. Okay. So it is one-legged, two-legged, one-legged, that's the way it is going. And the zero movement point is continuously shifting from leg to leg. It is starting at the heel, if you see, then it goes to the front, goes to the heel of the other foot. That is the way it moves. So because this is a dynamic system, the zero movement point is also moving. Okay. And we have to control it in such a way, we have to design the trajectories in such a way that the zero movement point stays on the foot on the ground. Okay. Now, it's interesting that if you look at the sole of your feet, okay, if you see the bottom of the sole of your feet, I hope you have seen the sole of your feet. Okay, if you haven't seen, please see it, not now, but maybe after the class is over, after you go back home or whatever. Okay, but you'll observe that the sole of the foot has a particular shape. And what is the shape? We have seen in this robot that the zero movement point starts on the heel. You can see the black dot. It is starting from the heel, going forward, then going out to the other side heel, then it's going to the front, then it's going to the other side heel. That means this point is moving, and it starts here, it goes like this, goes to there, and then goes to the other feet. This is the leg on ground. Okay. Now, if the zero movement point is going like this, which is also the center of pressure, it basically means that this part of the leg is supporting the zero movement point. The other part of the leg has no function. Okay. So if you see the sole of your feet, this is strong because the zero movement point starts there. This finger is big, is the biggest. Why? The zero movement point comes from here, goes there, then goes away. Okay. Whereas if you look at these small fellows, they are not supporting the zero movement point at all. So they have no function actually. And hence we have evolved, or the shape of our leg has evolved such that these fellows are small, that fellow is big. We can't do any work. The foot. It never goes to that side. And hence, if you see in your feet, on the bottom of your feet, there is no tissue here. So there is an arc and there is no tissue because the zero movement point is not required. The zero movement point never goes there. Okay. So our leg has evolved in such a way that it is essentially supporting the zero movement point. Okay. So this is another example of evolution. Two legs, shape of leg, energy optimality. Now we are seeing also that the shape of the sole of the feet actually has to do with the zero movement point. And if you look at your shoes, okay, where do the shoes wear out? Okay, when you're walking, the shoes will wear out here in that location. Your shoes don't normally get worn out that side. Why? Because this is where the zero movement point hits. Okay, so when it's coming from the other leg to this leg, this is the impact force, and that is the where it is going. Maximum stress is coming there. That is why in your shoes it also wears off there. Okay, so this thing, the shape of your feet, the way we are walking, actually has to do with bipedal locomotion, and we should understand what is balance because we also satisfy this. We have to satisfy, otherwise we can't walk. Okay, so it's not only for a robot. This is also how human beings work. Okay, we walk like this only. Now let's proceed further. How does the robot move forward? We have seen that the gait has one leg, two leg, one leg, two leg, that way. Now, if you're considering this to be a one leg stance, and this is the leg on the ground, okay, this leg is on the ground, then this is the rear foot. So it bends on one side, and the zero moment point comes onto the foot on the leg, which is on the ground. Then the rear leg moves forward like that. Okay, the rear leg moves forward, and the hip also moves forward because the whole body has to go forward, right? So the leg goes forward, and the full hip goes forward, as a result of which the body goes forward. That is how it moves forward. That is how we move forward. Now, in terms of robotics, the question comes, how many degrees of freedom? Okay. If I were to ask the question that you are walking, how many of degrees of freedom do you need for walking? Okay. So I'm not sure what your answer is, but if you think about it, to walk straight, only to walk straight, not to turn, you need 8 degrees of freedom. That means 4 plus 4. Okay. What are the 4? There are 2 here degrees of freedom in the ankle, 1 here and 1 here. Okay. So there is 4 and there is 4 per leg. So there is 8. So this will allow you to only walk straight, no turning. If you want to turn and walk straight, then you need 12 DOF. Okay, 10 is bad, but at least 12 degrees of freedom to enable you to turn also. Now, if you want to go on three-dimensional terrain like human beings on any kind of terrain, then you need 14 or you need 16. Okay. So this is giving you an example of that depending on whether you want to go straight, you want to turn on flat ground, or you want to go straight and turn on an three-dimensional terrain which is having all kinds of inclination. That will determine how many degrees of freedom you need on the system. That's one. The second is, so this is one point. The second point is the trajectory by which this is going. There can be infinite trajectories, right? The leg can go forward in infinite ways. Okay. Similarly, the hip can go forward in infinite ways. So why is it that human beings walk in the same way? Okay, we can have infinite trajectories also because it's a redundant system. Why is it redundant? Because it's 8DOF, and you know if it is more than 6DOF, it's a redundant system. Okay. So these are two questions we'll try and look at. So walking forward, how does it walk forward? First, it bends on one side. That's your degree of freedom. Degree of freedom that is coming. Okay, that's your degree of freedom 1. What is the second degree of freedom? This is your degree of freedom 2. In the side plane, now if I see this one is a degree of freedom, that is my 2. Then this is 3, that is 4, this is 5, this is 6, that is 7, and this one is 8 again. So 1 and 8 are across the axis are out of this plane because they have to turn like this as shown in this figure. Okay, the remaining fellows have to move in the side plane. Okay, so their axes are like this. Okay, they are parallel, but they are on this plane. This is how we are getting our 8 degrees of freedom. Okay, so 8 degrees of freedom for just walking straight, for straight walk only. Now, if you want to turn, you have to add more degrees of freedom. You have to add 1 degree of freedom there, and you have to add 1 more degree of freedom there. That's how it becomes. So 1 here means 1 here, and 1 here. This means plus 4. That becomes 12. You can walk with 10 also, but it's a very bad kind of walk. Okay, those degrees of freedom will come about this axis. So this will become our axis. Okay. Now, so this is how we basically walk. And so what we'll see next is when we're talking about these trajectories, they can be infinite trajectories. How do you choose a trajectory? Which trajectory is it going to walk? Okay. Now we can answer this question by saying that it should be energy optimal. Now the moment we say energy, how do you get energy? You have to do dynamics. Okay, dynamics will give you torque. Torque into that into the distance moved will give you the energy of the work done. Okay, so and this is very much in the purview of dynamics, and we model this like a serial arm. I'll just give a very simple example. So this is a serial arm manipulator. Okay, so this is a serial arm manipulator, let's say. Okay. So you have studied forward kinematics, inverse kinematics, and all that. And today morning we looked at dynamics. So when it is on one leg stance, this can be considered that the base is fixed, and this is the end effector. Okay, so the legs behave like an serial link arm only. So you can do the same DH parameter, assign DH parameters, do the forward kinematics, come from here, 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 up to there, do the inverse kinematics and get all the angles. So the modeling is exactly same as that of a serial arm robot. There is no difference. Now, once it changes feet, what you need to do is, if this is your 0, 0, 0, once it is on two-legged stance, you can switch the axis to the other feet. Because first it will be on one feet, then it will be on the other one, then it will come back. So the 0 is changing from feet to feet. Otherwise, it is modeled like a serial arm only. So we are assigning DS parameters onto each of the links. And you know this DS parameter assignments and transformation matrices. You can go from the base link. So 1 to 8 is from the base to the end effector. We can find all the matrices. Then we can do a forward kinematics, inverse kinematics. Okay. Now, what are the research issues? What are we going to talk about? One is energy optimal trajectory generation. So we'd like the robot to move around, climb, avoid obstacles. So how do you have energy optimal gait? Okay, that's one. Then, in terms of the design, can we make the biped soft? For example, can we put a soft sole on the sole of the foot? Okay. Then further, can we make the joints compliant? Can we make the joints a little bit soft by putting torsion spring? Okay. Then can we make the links itself compliant? So we start off with a rigid link. So this is rigid. Okay. Now these fellows are becoming soft we are adding flexibility on the system. We are making the sole soft. Okay. Then we're looking at compliance on the joints. We're making the joints soft. Then we're making the links soft. Then we're looking at motion planning in 3D. Why? Because if you look at the human body, our joints are not rigid joints. Okay, there is a lot of flexibility in there. If you look at the sole of your feet, they are soft. There is a soft tissue. Now, what is the advantage? And is that when we are walking, there is a lot of impact. So so it can absorb that shock, and it makes it safe. If a rigid joint is very rigid, if you hit something, what will happen? The joint will break. But if it is very soft, like the human, what will happen is you can absorb the shock very easily. The advantage of having softness or some amount of flexibility in the system. Now, in terms of optimization, I want to move this robot forward, having an optimal trajectory. So this hip trajectory and this trajectory should be optimal. Okay, optimal means it should take minimum energy. That is the trajectory I will choose. So how do we do that? So first of all, we make our dynamic equation. We write our dynamic equation, which I did sometime in the morning. And I'm modeling this like a serial link manipulator itself. So there's no difference. So tau is equal to the inertia term plus the Coriolis centripetal term plus gravity. I am ignoring friction and I'm ignoring external forces. Now the total work done is an integral, or this is a sum actually, of the torque into the velocity d theta into that time dt. So this is an integral, means torque into distance. Okay, so that is the work done. So if I want to find what is the minimum energy trajectory, what I do is I can put different trajectories. So let's go back there. So what we can do is we can put different trajectories onto this figure. Okay, so here I will put different trajectories, and for each of these trajectories I'll find the work done or I'll find the energy consumed. And then for whichever trajectory takes the least energy, I'll say that is an energy optimal trajectory. How do we do that? There are different ways of doing. You can do optimization using different methods. We have simply used GA. So GA is something very, there is a toolbox in MATLAB and the students all like to do GA. That's the reason we have done GA. Okay, no other reason. So the trajectories are generated by fitting different trajectories. So what GA basically does is we know the start point and we know the end point of walk. So when it is walking, if I draw it here, okay, so it is taking a start point and this is my end point. Okay, so similarly the hip is moving forward and the hip is moving here. So what I'm doing, I know my start point, I know my end point. So this is my start point, okay, and this is my end. Okay, so what GA will do is it will find two parameters in between. So this is one point, this is another point, and then it will form a spline between them. It can be a cubic polynomial, or it can simply be some of the spline function in there. So this is the trajectory. Okay, so what it is doing, it is shifting these points once here, once here. So by doing that, it is getting different trajectories. Okay, and for each of those trajectories, it is finding the energy. That is how GA works. And so what it is basically doing, it is just generating randomly these points, and it is forming trajectories, and then finding for those trajectories which is the minimum work done. Okay, and that is how we have done for, this is 8 degree of freedom, 8 DOF robot which can climb stairs, which can avoid obstacles, and you can get your optimal trajectory. So this is the optimal trajectory we are finding. Okay, so this is an S kind of a curve which is optimal. This is my obstacle, so that's my obstacle. So to avoid it, this is the trajectory which gives the least energy. Okay, so you can use other kinds of optimization, but this is what we have done. This is for climbing stairs. Okay, and it's interesting that our legs has 16 degrees of freedom. We have 8 plus 8. Okay, and if you see obstacle avoidance or stair climbing, human beings also follow this trajectory. Okay, so this has been proved that human trajectories are also optimal. Okay, so whenever we are going over obstacle, our leg will go up like that, then it'll go like this. So when we are walking, if you notice, please notice somebody else walking. Okay, or look at yourself walking in a mirror. Okay, what you'll note is that this leg goes up like this, it comes down like this, and then goes forward. This is called an S curve, and this is an optimal curve. So when human beings walk, we first take up our feet, it goes up like that, then it comes down, remains parallel to the ground, and then comes to stop. Okay, this curve is called an S curve, and optimally it has been found that all human beings use this trajectory only, and it is proved to be energy optimal. So in the morning I talked about energy ways of performing tasks using our hands. This is an energy optimal way of performing tasks using legs now. Okay, and all human beings do it like this only, because we are all energy optimal. Now moving on from here, we tried to look at the effect of putting soft material on the sole of your feet. Now, if you look at the sole of your feet, there is a lot of soft tissue. Plus, in our shoes, there is a soft sole. So when we are walking, this soft or flexibility has a large effect to play from the dynamics point of view and from safety point of view. So if you're looking at this, what you can see is that this is the sole of your feet. It is passive, so it behaves like a spring, and you don't have to give it any energy. So it basically means if you want to turn in, if you want to bend in this direction, you can bend it like this, and the deformation will be taken, your del theta deformation angle will be taken care of by your shoes itself. Okay, you don't have to give energy to do that. Okay, so this can save energy for bending. So we said that the biped robot has to bend first before it lifts its foot, it has to bend on one side. So when it is bending on one side, if this bending can be passive here, if this can be passive, then we can save that kind of energy. So what we did is we made a biped robot and we put soft material in the sole of the foot. And then we did force analysis to look at the deformations. This is a very simple model. This is a spring mass damper model, but it does show. So this is this is model like a spring. Okay, so there's a force, there's a spring here, and there is a deformation del x. Okay, so and the spring constant is k. So that is how it is modeled, how this material has been modeled. So this is a very simple way of doing it, but doing this this way of modeling, we can find the deformations. The deformation that is coming because of this material. And by changing the material properties, putting different materials, we can see how this is behaving. So this is exactly how it is behaving with different materials. So if the material is very soft, what will happen is it will start oscillating. Okay, this is intuitive, right? So if your sole is very, very soft, you'll not be able to control it. What will happen is you will start oscillating because it is extremely soft kind of spring. So there is some optimal value of that spring that is required, or the material that is required, that will give you stable kind of behavior. So we found that it is about, the value is about 6,000, okay, in terms of the flexibility of the spring. Now, does it save energy? Now, we saw that when it is bending on one side, because it is passive, it is saving a little bit of energy, because as shown in the figure here, it is bending on one side. This energy required to bend that much, del theta deformation, is coming from a passive material now, doing work to do that. So what is happening is we can save some energy, and we found that if you put soft material on the sole of your feet, you will end up with some energy saving. So with no deformation is 3.21 watts, and with the deformation is 3.16. It is very small, small saving, but then with every step or every half step, you get saving. So when you walk for very long distance or all through our lives, we are actually saving a lot of energy, just because our sole is soft. Now, from there, we built a robot, and this is the robot that. Oh, sorry, this is not working. Okay, so this was built, and it works by, and it has sole which can deform. Okay, so now beyond this, after this, what actually happened is it was observed that there is deformation on the sole of the foot. Okay, but then the way the biological systems are actuated, we have a muscle, and then we have a tendon, muscle, tendon, and the tendon is connecting to the joint. So in the hands or the legs, they are not directly actuated by the muscles. The muscles indirectly actuate the joints by means of tendons, and these tendons have some kind of stiffness. Okay, so they are elastic, they behave like springs. So again, two aspects. Number one is from safety point of view. So if you impact, because this is like a spring, it can absorb some kind of shock. The second is it stores energy because it's a spring. Okay, so when you're walking, running, jumping, you're actually storing some energy there, and this energy is coming back to you. So this kind of a structure into which we have evolved, okay, actually helps us in walking, running, doing tasks by means of providing safety and by providing some kind of energy saving. Okay. So now if you want to make a robot which is like this, and it has also been observed by others that birds like ostrich, for example, okay, which has a very strong run, it has a structure which is like this. So there is a muscle, then there is a tendon, and then the tendon is connecting to the bone. That is how it actuates. Now at the ankle joint, there is a tendon there which is connected to the muscle. Okay, so these tendons, basically, which are springs, have a big effect on walk and run. So what we tried to do is we tried to make a biped robot which has springs in the joints, and if you put springs in the joints, it behaves like the tendons. Okay, so our objective here is tendon is replaced by a spring, torsion spring in this case. So how is the construction looking like? The construction would be a motor. Okay, the motor has a gear in front, encoder at the back. Then the motor is connected to a spring. The spring can be in the form of a springy shaft. Okay. Then on the other side, it is the link. So that's my link now. Okay. So in between the link and the motor, there is a spring now. The spring can be in the form of a torsion shaft also. So when it so there is a torsion shaft which can take which has some deformation about that axis, which is del theta. Okay, so we have added a spring which is basically to replace the or to replicate the motion of the tendon. If you write our dynamic equations again, so the spring fellow will come inside now. So F is equal to K into X. A very simple model that we are using is F is equal to K into del X. Okay, so this is the model which we are using here. So in our dynamic equation, we have ended up with the spring coming inside now. So it is minus K into theta minus theta R. Okay, so this is my dynamic equation now. Now again, same way, you can find optimal trajectories with spring and then look at what spring stiffness should be there to be able to give us the least energy requirement. And I just explained that you can model it by, you know, the start point, we know the end point. We can fit different trajectories by choosing different points, put a polynomial or a spline, and using dynamic equation, we can find the work done. And whatever trajectory gives the least work done, we can say that is the least energy trajectory. Okay, so if you do that, what we do find is that for different values of K, now K is the spring stiffness, the trajectories are different. That is expected, right? That if you put different kind of springs, the optimal energy is also going to change. But what is interesting to note is that for different values of K, this is giving me different values of K, different values of stiffness K, and this is what that appears to be an optimal stiffness. Okay, so if you put a stiffness which is higher than this on this side or this side, okay, then what we find is that the work requirement goes up. Okay, so there is some kind of an optimal spring stiffness that is required to get minimum energy. Now, where is the problem with this? The problem with this is that the leg is on two stands. The leg is here, the leg is in air. One leg is in air, one is on the ground. Okay. Now, the one on the ground has to support the full forces and moments which are coming. The leg on the air does not have to support the moments and forces which are coming. Okay. Now, on this half step, this leg is on the ground, that is in air. But the next step, what will happen? It will reverse. Okay, if I draw it here, okay, this leg has gone in ground. Now this fellow is in air. So this fellow needs to become stronger and have higher stiffness. So this is fine, but then this has to alternate because the leg on the ground needs more stiffness and the leg in air does not need stiffness. And that is a challenge in today's robots. Now, interestingly, in the human system, it has been observed that we can change our stiffness. So this is our stiffness of the tendon. This can be changed or this can be switched. And hence, in the human biological system, it's a variable stiffness. Okay. So we can change our stiffness depending on whether we are running, we are jumping, we are walking, on whether we are pushing an object or we are pulling an object. We can just change our stiffness the way we want. Okay. But for a mechanical system, for a robot, this is extremely difficult. Why? Because if you put a spring, what will happen is the stiffness of the spring will become constant. And if the stiffness of the spring is constant, then you cannot switch it. Okay. So this is a major challenge in trying to make robots which are like this, having some kind of soft in the in the joint. Okay. Now, in terms of control, there are something which are called series elastic actuators. These are topics which are very important these days because a lot of people are working in terms of research. Series elastic actuators. Okay. What this series elastic actuator is, it is something like this. So there is an actuator which is a motor, then there is a spring, and then there is the link, and they are connected in series like the way I have drawn it. Okay. Now, what is the problem in terms of control here? You have one input here, but you have two outputs. What are the two outputs? One output is here. You have theta of the motor, theta m, and the other side you have a theta L, and theta L is not equal to theta m because there is a spring inside now. So you have one input which is a voltage to the motor, but you have two outputs which is theta m and theta L. So in reality, you cannot control the system. okay, because your input is V and your outputs are theta L and theta M. Okay, so this is one input and two output system now. Okay. So in terms of control, this is what happens. If you start putting something which is flexible in there, it will start making your control more and more difficult, which means that it is going to start introducing vibrations. Okay, it can lead to instability. So what is done is basically they put a sensor onto the other side also. So there is a sensor here already, there is an encoder in the motor, but they put one more sensor here and then use a backward loop. Okay, so the way people try to control series elastic actuators is by putting two sensors. One is for the motor and one is for the link, and then either to have feed forward a control loop. Okay, so in terms of control systems, this is a difficult control problem because the moment you make something soft, it becomes a single input two output system now. Okay, so this one is basically showing us about the introduction of a spring and the effect of the spring. Now let us move further. What we basically try to think about next is if we put us, so first we started off with the rigid link biped, then we put a spring. So first there was a rigid link, then there was a spring, there was a soft sole which was put there. Then we put spring, so this is point number one. Point number two is spring, okay? And we found that it does save energy, but it makes control a little bit more difficult. Now, what would happen if I make the link itself flexible? Suppose I put a flexible element there. I remove this rigid link and I put a flexible link now. Now what will happen? Okay. Now, this has advantages. Advantages means when it is running, when it is jumping, this behaves like a spring. Okay, so you can imagine if you have a semicircular beam like this and you put forces, what will happen is it will deflect. Okay, it'll deflect. The moment it deflects, okay, it will behave like a spring. Means deflection means what? It is absorbing energy and it's giving back the energy. So when you're running, it will absorb that shock and will give back the shock. So you'll save a lot of energy. Okay, but you'll end up with this kind of unstable kind of issue. So the next thing that we did is we made the links compliant. Okay, so the next, let's move on. So bipeds with compliant links or flexible links where the links itself are compliant. So this is a rigid link biped where the link is rigid. So we remove this link and we put a compliant section, a semicircular semicircular section there made of aluminum, which is behaving like a torsion spring. So if you look at a torsion spring, it's like this. So if I take the torsion spring and I cut it here, okay, so I cut it here. So what you'll get is this section. So this is also behaving like a spring only, right? So that is my torsion spring. So now only this section is semicircular section like this, and this will also behave like a spring only. If you give force there, it will deflect. Okay, it will start deflecting like this, right? And that will save energy when we are walking. So what we did is we removed the leg section, the rigid link, and we put a compliant section in there like this. So this is my compliant link, which is semicircular in shape. It's made of aluminum, the particular thickness, so that it can deflect. Now the question that comes up here is what should be the shape? Okay, so there is some optimization at every step involved. What should be the shape? Should it be like this? Should it be like this? Should it be like this? Okay, should it be like this? Now, the shape should be such that it is going to save the maximum amount of energy when it is walking. Okay, and then what we found is that the semicircular fellow is the one that has the maximum deflection, and that is the one that we used because maximum deflection would mean that it is taking energy and giving back energy, the maximum amount of it. Okay, so so this is the basic model where we have the rigid link being replaced by a compliant link, and we have a compliant link biped now. Now, when we are making it work, we have to give two trajectories. One is the hip trajectory and the leg trajectory. So as I explained, the hip trajectory in this case is a sinusoid. We are putting a sinusoidal trajectory on the hip, and the leg trajectory is also optimized by using GA. Okay. Now, there is a little issue here. Now, what is the little problem here is that you have two equations in terms of dynamics. This is one equation for rigid link biped, rigid link robots. Okay, so there is one equation. This is for the active joints, wherever there are motors. But the spring-like flexible link does not have a motor. It's a passive element, right? You cannot control it. So you get another equation, which is K into this is my spring equation, F is equal to Kx. Okay. Now this is equal to 0, which means that you cannot control the flexibility, you cannot control the deflection of the link. So what I mean here is I have a force which is acting at the knee joint. Now how much deflection will come, you cannot control that. It's a system property. Yeah, it's a material property now. Okay. So if I give some force here, corresponding to that force on this equation, the deflection will come. You cannot control it. So to solve this equation, we have to go in two-step procedure. First is you solve this equation, the dynamic equation, find out what is the torque acting at the knee. Then that is for a rigid link biped. Then for that corresponding force on the knee, find what is the deflection by using this equation. Now, once you have incorporated the deformation, the link angles have changed. So you have to do the dynamics again. Okay. So this is something like a two-loop process. Assume that it's a rigid link biped, no deflection. Do the dynamics, find the forces acting at the knee joint. Then assume that the forces are going to cause a deflection at the knee. And for that corresponding deflection, what should be the corresponding dynamic forces again? So it is some kind of a loop that you have to follow to do this. And I talked about one input, two output system. So this is basically showing that there are two equations, but there is only one input. That is my top. Okay. So this kind of a control system is difficult to control. Now, in terms of the inverse kinematics, something interesting here is that for the biped robot, it looks difficult, but it's not. If you look at the geometry of the system, let me look at here. If I look at the geometry, let me just explain this because it is very simple and anybody can do that, but you just need to understand that. Okay, this is the leg on the ground, this is leg on ground. Okay, this is the other legs. So when the leg is going forward like that, the hip is also going forward. Okay, so if after GF finds the trajectory, you can divide the trajectory into 20 points or 30 points.
Sir, you are not audible. Sir, yes, sir. Now you are audible,
Yeah.
sir. Yes, sir.
Yeah, I'm audible. Yeah, I think something cut. Anyway, I have to start sharing again. Okay, now is it okay?
Yes, sir. Yes, sir.
Okay, okay. So I'll just repeat this quickly. What I was saying before it got cut is that when we are walking, basically we are looking at these two trajectories. So what GA is doing is it is generating different trajectories, and for these different trajectories, what we are doing is for each of them we are dividing this into 20 points. Okay, and the hip trajectory and the leg trajectory we are dividing it into 20 points, and for each point correspondingly we are joining them with the with the legs. So what I'm saying here is that this is my leg, this is the hip has moved like this, the leg is moving like this. So this point and this point, if I join, it is like this. Next point is joined, it is like that. Okay, this is how the leg is moving forward. And if you look at this, this is a two-link system. And you know the inverse kinematics of a two-link system. So from geometry, we can solve this very easily. Okay, so it is 8 degree of freedom or 16 degree of freedom. It looks very complicated in terms of geometry, in terms of inverse kinematics, but actually it's not. Why? Because if you're looking at the hip trajectory and the leg trajectory, in between the hip and the leg, there is the legs, which is basically a two-link system. So you can very easily solve this from geometry itself. Okay, so this is the geometrical solution. So this is my two-link system. This is the hip trajectory, this is the leg trajectory, two links. So you know what is this angle, you know what is that angle. From geometry, it's very easy to get that. Okay, so although it looks difficult, it's not. Okay. Now, so what we are trying to do here is we have to write a dynamic equation, find the torques acting at the knee joint. For the knee joint, we have to find what is the deflection, and based on the deflection, we have to compute the dynamics again. Now, how do you compute the deflection? We have to do finite elements. There is no other way out. Okay, so we have to do finite element analysis and break up this into different nodes. And each of these nodes, you have to find what is the forces and moments acting on the nodes, and then we have to sum it up. We have to sum up the deflections. So we have, this is my knee joint. From dynamics, I find what is the force acting at the knee, and then I find what is the deflection corresponding to this force, and then see what is the joint angle change and find the dynamic forces again. Okay, so this is basically our FEM analysis. I will not go into this, there's no need. We break it up into small nodes, and then we find the deflection of each of the nodes. This is my stiffness matrix. Now, doing that, what we did find is you can find the optimal trajectory for a compliant robot also. So this is a compliant robot, which has one of the links which are flexible, and this is the optimal trajectory. So if you can see that the trajectory appears to be an S-curve also. Okay, so this fellow also has a human-like trajectory, which is S-curve. Now, if you see the top view, so if I look from the top, we can look at the feet like this. So this is the right foot. So this is the right foot, and there's the left foot. And this is the motion of the zero moment point. Okay, the zero moment point is moving like that, and the center of pressure is moving, is the green one. So both of them are on one foot, then it goes on the other foot, then it comes to this foot. Okay, so you can see that the zero moment point is doing like this. Now this is for a rigid link system. Okay, so if all the links are rigid, then we find this is the pattern of walking, and this is the trajectory of zero moment point. Now, something I forgot to mention is that when you're doing the optimization, the zero moment point is the ZMP is a constraint, because it always has to be balanced. So whichever trajectory is being found, the trajectory has to satisfy zero moment point condition. Okay, otherwise the biped will fall. So when the GA is being run, the objective function is the work done, and the constraint is the zero moment point. So whenever it is violating the constraint, that trajectory is rejected automatically. So these are all feasible trajectories. This is an optimal feasible trajectory. Now, in the case of the compliant robot, when we try to do that, what we found is that the zero moment point starts fluctuating. So you can see that it's not straight anymore. It is vibrating in between now. Why? Because I put a flexible element now there. And this is what I was talking about, a series elastic actuator. The moment you do that, you're introducing a passive element. Now there is a problem in control. Now, this is also the trajectory of the biped for going up a slope. So it is going up inclined surface. This is how it moves. You can see that it is circling there. Okay, what it did, it went forward, then it made a turn, and then it did all funny things. This is the biped walk of a rigid link biped. All the links are rigid. Okay, it is walking. Okay, two leg stance, one leg stance. Okay, then what we did is we changed one of those links to a compliant link. So this section, I'll make it compliant. So I'll put a compliant C section there. Okay, and then make it walk and see what it is doing. So this is my compliant section. Okay, with this one, when it is walking, you can see that a lot of vibrations have come inside now. It is the whole robot is shaking. So when it is on one leg stance, what is going to happen is it will start shaking a lot. Okay. So this is showing the effect of putting that compliance. But what is the advantage? The advantage is that you're saving energy, and especially in high dynamic tasks, for example, while jumping, while running, this C section is going to absorb your energy and it will give back the energy. And it's also safe. Okay. So this is, it has advantages. It also has disadvantages. And interesting that biological systems have some amount of compliance in our joints because we are required to absorb shock. We also have energy saving. We also have optimal trajectories. So this is something that is interesting. For research, it is good because the moment you put vibrations, you need to control vibrations now. You need some kind of active control. You need better controller design. So for research and for PhD students, MTech students, it's a very good idea. You can do a lot of research in this. Okay, but this is basically to show what happens if you put compliance in your system now. We track the trajectories, and what it is showing is that the trajectories are not uniform or not very smooth, but they have all kinds of jerky motion. That was expected. Okay, but so there are advantages, disadvantages. This is still a research problem. Series elastic actuator in the world is today still a research problem. A lot of people are working on it because the requirement is in robot-human interaction. A lot of robots are being made where there is some amount of flexible element in the joint. KUKA robot has made robots which are safe. Why are they safe? If they hit something, what will happen? The shock gets absorbed. So they will not hurt anybody. Okay, but they introduce this kind of instability in the system. And we can look at the zero moment point. We saw that it was vibrating like this. Okay, it was not steady anymore. Now let's look at the last issue here in biped locomotion. These are some research issues. One of the issues in biped locomotion is whatever I talked about is on flat ground. Okay, so generating trajectories, then soft sole, then looking at compliant joints, looking at compliant link. This is work on flat ground. What do I mean by flat ground? Geometrically speaking, this is my ground, and if I divide it into grids, okay, all the vectors pointing upwards. This is the definition of flat ground. Okay, a flat surface. Okay, the vectors will be all perpendicular to the horizontal. The moment we are not on flat ground, we are on uneven terrain. What does that mean? That means that if my vectors are like this now, okay, so now they can be in any direction. So this vector is this side, pointing this side. This vector is in this side. Okay, this vector is this side now. Okay, so now these vectors, normal vectors, in each of the grids are making angles with the three axis x, y, z. Here it was just 90 with respect to the horizontal. This is what I mean by 3D. So whatever I talked till now is basically on flat ground. This is flat ground. So the moment it becomes on 3D, then there is a big challenge in balance. Okay, because that zero moment point concept doesn't work in 3D. It works only on flat ground. Okay, because we are making the assumption that the forces coming from the ground are the reaction forces from the ground are balancing the forces coming from top. That's an assumption. Okay, so it is only for flat, but in case it is 3D, the robot could be standing in such a way that it is not balancing anymore. So balance in 3D is still an open challenge today. What we tried to look at it here is, I will just talk about in terms of motion planning. That is, I want to go from one point. So I want to go from here to here, find a path, walk on the path. This is one problem, avoiding obstacles, which are these. The second is, suppose there is a ditch, this 3D ground, and there is a ditch like this. Okay, I want to cross the ditch and go from here to here. How do I do that? And what we did here is basically using the Econol equation, which is a wave propagation equation. Now, how this wave propagation equation works is, this Econol equation essentially is it solves the path of ray of light, which is traversing through mediums having different refractive index. So if there is a ray of light which is traveling through mediums which have different refractive index, then it will change its direction. Okay, and that's the same thing we are doing here, and it works like a wave propagation. This is a wave propagation equation actually. So wave propagation. Okay, so in a pond or in a lake where there is water, if you drop a stone, what will happen is waves will be generated. And how do the waves propagate? So first, the wave will be generated where you drop the stone, then the waves are going to propagate like this. Okay. So this equation is basically governing your wave propagation now. Now, which direction the wave will propagate the most? The direction in which there is no obstacle, okay, or where the gradient is less. So by solving this equation, basically, we are basically forming a wavefront for a generator. So this is a wavefront generator. It is generating waves, and whichever direction the gradient is less, the waves are going faster in that direction. Okay. So basically, by solving that equation, we can get an idea of the terrain, or we can include the terrain geometry into the walking pattern generation. So what we did is we incorporated the dynamics of biped walk along with the terrain geometry. The terrain geometry is being included by looking at the height of the terrain. Okay, so corresponding to here, this is higher. Now it has normals, so these normals are making angles. So we're looking at those angles. So by looking at that, we are making a speed function basically, which is saying that if whichever direction it can go the wave can go the fastest, it will go in that direction. It will not go towards the high region, or it will not go towards the obstacle region. Okay. So very briefly, this is what we have done by incorporating the biped dynamics along with this the terrain geometry, and then we solved the wave propagation equation. And what we get is this is a case where you have obstacles, okay, and the terrain is three-dimensional terrain. So all the gradients are taken into consideration, and then it can optimally find this path and it can walk. Now, to do this kind of optimization, for every step, it takes a lot of time. It takes few minutes. It cannot be done in real time. So dynamics cannot be done in real time. Okay, so we have to use some kind of learning. So we have to generate large number of data sets and then basically learn it using neural net or whichever learning method. And then once it is learned, then we can make it work. Okay, so this is where most of bipedal locomotion research is today. So these are this is a case of three-dimensional ground. This is a biped robot which has learned to walk, okay, and it can walk on the terrain optimally by finding optimal trajectories to go from one point to another point. Okay, so this is an example of three-dimensional terrain. You can see that the gradients are different in every grid, and it has to optimally find its path from one point to another point and then go there. Okay, it is doing dynamics. It has done dynamics, generated a data set, learned the data set, and once it has learned, then it is real time. Neural net can operate in real time, but the learning takes a lot of time. It takes hours and days sometimes, because there is the data set is very, very large. This is another case of the robot walking. This is the case of ditch crossing. Again, this is three-dimensional, and the robot has to go from one point to another point and cross this ditch. Okay. Again, it is using a learned data set. It has learned to walk on any kind of condition. Okay, and it can find out which is the narrowest section of the ditch, and then it can cross the ditch, go to that section, cross the ditch, and then go to the other side. So in the beginning of the presentation, I had shown the Atlas robot, which is walking in ice. Okay, and there is a lot of deformation on the ground, and the terrain condition is bad. Okay, that is where research in bipedal locomotion is today, where you have to incorporate the system dynamics, you have to incorporate the deformation on the ground, and then find optimal trajectory and then make it work. Okay, so this is a case of ditch crossing. This is another case of ditch crossing, where the robot is walking from here and crossing a ditch and then going on to wherever you are. Here again, the ground is 3D, but it is rigid ground. There is no deformation. The moment it becomes ice or sand or mud or clay, grass, for example, there will be deformation on the ground now. The moment there is deformation, plus it is 3D, that's the most challenging. Okay, and that is where bipedal locomotion research is today, where people are trying to find solutions for this problem of bipedal robots walking on soft ground, on uneven ground, and any kind of ground. Okay. So I think I'll stop today. Okay, before I stop, the future directions biped research. One is balance. We said that there is zero moment point, but it is valid only for walking on flat ground. Uneven ground doesn't work. So people have used things like center of pressure. What do human beings use? Do human beings use this? No, human beings use center of pressure. So on the sole of our feet, Okay, if I draw the sole of our feet, so this is our foot. This is a very fat foot. Okay. So if I draw our foot, on the sole of your foot, there are pressure sensors. Okay. So what we do when we are walking is we look at the center of pressure. So we see if the zero moment point is here, the pressure here will be higher. So we know it is there. Okay. This is how we walk. So we are using center of pressure, not zero moment point. Okay. But for a robot to put sensors on the foot and then to do the signal processing and then do dynamics, it's not possible. You can't do it in real time. Okay. So what people have suggested is to go for extended zero moment point and then a foot capture point. Foot capture point is something like an inverted pendulum. So suppose there are 2 feet here. Okay. So there is 1 foot there and there's another one here. Okay. So when it is moving forward, it tends to fall. So to prevent this fall, this leg should move forward and block that fall. And that is basically called foot capture point. The Atlas robot walks by using foot capture point. So balance is still not well understood in 3 dimensions. So this is an open area, mechanics, dynamics. Humanoids living with humans. Then biped locomotion in real world. Okay, human-like behavior and intelligence. So this is the direction of bipedal research today. Okay, so what I'll do is I'll stop today, and then if there are any questions, I'll take the questions. Okay, so I'll stop. So are there any questions?
Participants, you can ask your questions, please. I would request all the participants, if you have any query.
Hello. Yes, sir. Very good afternoon, sir.
Good afternoon. Yeah.
Sir, myself, Dr. Anil Kumar Gilawat. Sir, I was asking about that bipedal. You were talking about that. Is it easy to solve with that serial manipulator or parallel manipulator?
No, it's not well, it is alternating between parallel and serial. Okay, so when it is on 2-leg stance, it is parallel. But when it is on 1-leg stance, it is serial. Okay. But when it is moving forward, it is on 1-leg stance. So it is serial. Okay. So it is easier to solve it this way.
And sir, that you were talking in the last lecture that Newton-Euler method you were talking about, and that you find out that relation between the ith link and I+1 link, and that can we use it for defining that velocities and position analysis also?
Yes, because in the Newton-Euler or Lagrangian-Euler, your input is your joint velocities, right? Joint position, and the derivative will be the joint velocity.
Yes.
Okay. So you have to define that, and that actually comes from the trajectory. So I did not say it here, but yeah. So how do you get that? Is essentially when it is walking. Okay, we are. Let me draw it here. This is my trajectory, right? Okay. So in the trajectory, I'm dividing the trajectory into 20 points, right?
Yes.
So every point is corresponding to the other point for the hip and the leg, right? At the trajectory. Now, if you do inverse kinematics, when it is moving from here to here, the joint is also moving by a small amount del theta. So this is what I mean by velocity, incremental velocity. Did you follow?
Yes, sir.
So
we are changing that increase in the velocity, no, sir?
Yes. So it is the del theta actually.
It is a combination of angular velocity and linear velocity, both, no, sir?
Yes, but how do you get it? Because when you're optimizing, you're finding the trajectory, right?
Yes,
we are optimizing by finding that optimal trajectory. So for every trajectory, what is the meaning of velocity? It means that when it is at this point, it is going to the next point, then the next point, then the next point. This is in Cartesian space. This is the XYZ. So if you do inverse kinematics, you can go to the joint space, whereas the thetas are there at the joint. So when it is going from here to here, what is that change in the theta? That is my theta dot.
Sorry.
Okay, so these are the incremental velocities. That's how you find the velocities.
Okay, sir. Thank you, sir.
Any other question? Or everybody is hungry? Okay, we can stop then.
Thank you, sir. Thank you so much for giving us your valuable time, sir. And it's a really enlightening and very informative session. I hope participants might have enjoyed this session, and in this session you have nicely explained about the biped locomotion in a very simple way, so it will give a better and clear understanding to all the participants to do research in this emerging area. Thank you so much, sir.
Okay, thank you and bye.
I would request all